One of the difficulties with current theory, cold dark matter theory, sometimes it's abbreviated LCDM, one of the problems with it is just simply testability, because it's positing all of these exotic energies and masses out at distances where we really cannot detect them. We're talking about intergalactic distances. So obviously, I mean, there's no possibility of sending a probe to test and see if these things are there. Also, the densities, the purported densities of dark matter, like here in our own solar system or in our own galaxy, the densities are so slight that they're positing. And the fact that dark matter, as posited right now, doesn't interact in any way except by gravity, and gravity is such a weak force. So it's, practically speaking, impossible to test current LCDM theory. There is no practical, easy way of testing it to prove that this dark matter, dark energy is there. Now, this hypothesis I'm putting forward, on the other hand, because I'm positing gravitational effects that we could observe right here in our solar system, there are ways that it could be tested, and either this idea can be confirmed or else it can be falsified, probably with data that we already have right now. It just a little different analysis of the data needs to be happening. So I'm talking about data with having to do with asteroids in our solar system, any asteroid with an eccentric elliptical orbit, or comets within our solar system, or probes of various sorts within our solar system. So once again, here's a graph of the equation that I've come up with, and I want to emphasize again that this equation is just a first approximate guess, kind of like a trial, and so reality might not be like this at all. I mean, I'm positing peaks here, this is Mercury, and then this is Venus, this is the Earth. So these places where I'm positing peaks and troughs, in reality, might be very different than what I'm showing here. So this is just a first guess. But my point is that we should be able to analyze the acceleration of objects in these areas between the planets to see if the acceleration caused by gravity is wildly different than what current theory is expecting. So this is a picture of the orbit of Etira 2019 LF6. This is an asteroid that has a very elliptical orbit. It sometimes is closer to the Sun than Mercury, and sometimes it's out near the orbit of Venus. And so this asteroid would actually travel through regions where I suspect gravity varies greatly and even becomes negative in some of these regions. Now, the way they come up with a plot of the orbit is they more or less just use its position at various times and then plot its orbit based on current theory. But what I'm contending is that if we were to look at this asteroid moment to moment as it goes on this path, from moment to moment, we would see its moment-to-moment acceleration deviating from what current theory is expecting. So we would see a pattern of acceleration and deceleration throughout this orbit at various places. And the same thing with Halley's Comet, its orbit shown here. And this is the orbit of Pluto. Now, very close into the Sun are all the inner planets. I mean, in here we have from Jupiter all the way down to Mercury in this little tiny area here. But my point is, Halley's Comet goes on such a eccentric ellipse that it would pass through many different regions that I'm talking about where there would be negative gravity. And so once again, if we look at the moment-to-moment acceleration of Halley's Comet, or any comet like that with a wild elliptical orbit, we would see a pattern of acceleration and deceleration in the data. And I believe that we may already have the data to be able to do this analysis. Similarly, here I've kind of shown a not to scale the orbits of all the different planets. Here's Saturn, Jupiter, this is the asteroid belt, here's Mars. And my point here is kind of in this yellow highlight, I put where regions may be repulsive gravity. And once again, if we look at the telemetry, all of the data of our probes, various probes like Pioneer or Cassini, or any of the probes we've sent out that pass through these regions, if we look at the moment-to-moment acceleration data for their probes, we might see some kind of pattern like this. Now again, when I did my equation, I set it up in such a way where I was just guessing that we had a repulsive region in between each of the planets, but obviously I don't know that for a fact. The pattern of repulsive attractive gravity might be quite different than I'm speculating, but my point is, if there is a pattern of repulsive and attractive gravity in our solar system, we should be able to find that out by analyzing data that we already have.